Now discussing about the open organ pipes. Open organ pipes are the musical instruments which are used for producing sounds when air is blown into them. Now these open organ pipes, unlike closed organ pipes, are open at both the ends. So in these pipes, the standing waves or the stationary waves are produced by the incident and the reflected waves, but those waves are reflected from an open end. That means there is a phase difference of 0. Let we take a wave that is traveling in positive x direction. Let that be y1 of xt, and that be equal to a, where a is their amplitude, a sine of omega t minus kx. The minus sign because it is traveling towards x axis. Now from an open end it gets reflected with a phase difference of 0. That means compression is reflected as a rarefaction, or rarefaction is deflected as compression. So the reflected waves equation is y2x comma t is a sine of omega t plus kx, as the reflected wave is traveling in negative x direction. Now by the superimposition or superposition of these two waves, a standing wave is produced. So y is equal to y1 plus y2. So y x comma t is equal to a, getting a common, that is sine of omega t minus kx plus sine of omega t plus kx. Now this is the formula, sine A plus sine B, and we know that sine A plus sine B formula is twice sine A plus B divided by 2 cos of A minus B divided by 2. Applying the equation here, we get a twice sine a plus b, so omega t minus kx plus omega t minus kx. Adding these two, we get twice omega t, kx and kx cancels, divided by 2, and cos of omega t minus kx minus omega t plus kx. This omega t and omega t cancels out, minus kx and minus kx is minus twice kx divided by 2. So 2 and 2 cancels here, 2 and 2 cancels. We also know that cos of minus theta is equal to cos theta. So here yx comma t is equal to 2a sine of omega t cos of kx. This is the formula for the stationary or standing waves in open organ pipes. This is different from the closed organ pipes and the standing waves in strings tied at both ends. In those two cases, the equation of yx comma t is twice a cos omega t sine of kx. Now replacing yx of t by sx of t, because sx of t gives us a field of longitudinal stationary waves. Yx of t is used for transverse standing or transverse stationary waves. Now we know that at open organ pipes we are having an antinode at both the ends. That means at x is equal to 0, at x is equal to 0, that is here, and x is equal to L, and x is equal to L, S is maximum. The value of S here, maximum value, is plus or minus 1. So in order that S should be maximum, this cos kx should be maximum. Putting in this equation, so we have cos of kl is equal to plus minus 1, and we know that the value of cos of theta is plus minus 1 when it is integral multiple of pi. That means it is equal to cos of n pi. Now this cos and cos goes, k is propagation constant, so 2 pi by lambda into L is equal to n pi. Pi and pi goes, so lambda is equal to 2L divided by n. Equation for finding the lambda in different modes is 2L divided by n, while n is the number of mode or number of harmonic and L is the length of the organ pipe. So lambda is equal to 2L divided by n. we will go for the first harmonic. First harmonic or the fundamental mode. For first harmonic or the fundamental mode, n is equal to 1. That means lambda is equal to 2l, or lambda 1 is equal to 2l, or we see that L is equal to lambda 1 divided by 2. What this tells us? It tells us there is half a wavelength in first harmonic or fundamental mode in the entire length L. So we are having this way. So we are having antinode here, and node here. This is a quarter wavelength, this is a quarter wavelength, two quarter wavelengths make half a wavelength. This is a quarter wavelength, this is a quarter wavelength, two quarter wavelengths make half a wavelength. So in the length L of the open organ pipe, we are having lambda divided by 2, half a wavelength. Now we will see the frequency. The frequency is of the frequency of the fundamental mode is velocity divided by lambda. So nu1 is equal to V divided by 2L. It is the frequency of the fundamental mode. Going for the second harmonic or the first overtone, here n is equal to 2. So lambda 2 is equal to 2L divided by 2. So lambda 2 is equal to L, which confirms that in the second harmonic or the first overtone, we are having a full wavelength in the length of an open organ pipe. This is quarter wavelength, this is quarter wavelength, this is quarter wavelength, this is quarter wavelength. So we are having a full wavelength. Similarly, from here, this is a full wavelength in the length L. The frequency of the second harmonic or the first overtone will be equal to nu2, that will be equal to V divided by lambda 2. So nu2 is equal to V divided by lambda 2 is equal to L. So we can say that dividing and multiplying it by 2, we have it as twice V divided by 2L, but V divided by 2L is the frequency of the first harmonic. So frequency of the second harmonic is 2 times frequency of the first harmonic. So frequency of the second harmonic is 2 times frequency of the first harmonic. For third harmonic, n is equal to 3. So lambda 3 is equal to 2L divided by 3, or we can say that L is equal to 3 by 2 lambda 3, which brings us to the conclusion that in the third harmonic, in the length of the open organ pipe, we will be having 1.5 lambda. That means a wave and a half. The third harmonic can be shown by this. This is 1 and a half wave, having antinodes here, here, here and here. Nodes here, here and here. Going to the frequency of the third harmonic, nu3 will be equal to velocity divided by wavelength of that mode, that is lambda 3. That is equal to V divided by lambda 3 is equal to 2L by 3. It is 2L by 3. This 3 goes up, that becomes 3V divided by 2L. Now we know that V divided by 2L is the frequency of the fundamental mode. So nu3 is equal to 3 times nu1. From the discussion, we see that we are having all the frequencies. In fundamental mode, frequency is nu1. In second harmonic or first overtone, frequency is 2 times nu1. And in third harmonic or second overtone, we are having frequency 3 times nu1. So it is the integral multiple of fundamental frequency. We can generalize the equation for frequency of the nth harmonic as nu(n) will be equal to n times nu1, where n is the mode number or harmonic number and nu1 is the frequency of the fundamental mode. From that discussion, it is also clear that in the closed organ pipes, the number of nodes is equal to the number of antinodes. In the fundamental mode of the closed organ pipes, we are having one node and one antinode. In the second harmonic, we are having two nodes and two antinodes. But here in open organ pipes, for the nth harmonic, we are having n number of nodes and n plus 1 number of antinodes. That can be exemplified by a simple discussion. Here n is equal to 1. This is the first harmonic, so number of nodes is equal to 1, number of antinodes is equal to 2. In the second harmonic, number of nodes is equal to 1 and 2, and the number of antinodes is 1, 2 and 3. That means for nth mode we are having n nodes and n plus 1 antinodes. For the third harmonic, node number 1 is this, node number 2 is this, and node number 3 is this. We will be having n plus 1, that is 3 plus 1 antinodes. Antinode here, antinode here, antinode here, and antinode here. So it is clear from the discussion that in the nth harmonic of an open closed pipe, we are having n nodes and n plus 1 antinodes. Hope you understood.